Hi and welcome everyone. My name is Steve Teresi. I'm the VP of Technical Services here at JL Audio. I am joined with my buddy Matt here in our facility in Miramar, Florida. Say hello, Matt, again.
Hello, Matt, again.
There you go. And as always, we have Mr. Rob Haynes joining us from Southern California. Please say hello, Rob.
Hello, everyone. And I was going to add Matt's name just now to your title, but I don't know how to spell Mergenthal.
Yeah, well, I'll try to make a change during our session today so Matt gets some kind of credit for being here. So let me... I'm going to read off my little script here for some of the things that we have to cover today. We're talking about transfer functions as a carryover from our last session. Today, we're going to focus on electrical measurements. We're going to talk about being able to do Oem integration as part of the measurement system for using Macs. We're going to look at the difference between an input and an output on a source unit. So you have something that comes into a source unit, and you can look at the output of that source unit and see what's going on. We'll be able to compare left and right. And what's really cool about this, there's no way to hide data. When you have a measurement system that can look at all three dimensions of audio, the magnitude, the level, and of course the time or phase aspect of it, you can see all the things that'll change in any of the magic boxes that you may have access to. So what Matt's going to do for us is going to guide us through taking tons of different electrical measurements using Macs and various different sources and probes and all kinds of fun stuff. So I'm going to turn it over to him and let him take it away. Go for it, Matt.
Well, hi, everybody. I'm excited to be here and show you some cool stuff today. So I'm filling some big boots for Nick Ames, who is unavailable at the moment. So first, what we're going to do here is we're going to look at the input versus output of a radio that we had laying around. So how we've done this is we've routed signal from the outputs of Macs, the RCA outputs, going into the auxiliary input of the radio here. So what we're going to do is we're going to look at a couple things. We're going to look at the time related to the radio, as well as the frequency response to the outputs and see what's happening there. So as previously stated, we already have our auxiliary input going into the radio. And then on the output, we have a set of probes that are connected to the RCA output. Here, as you can see in tune, we have input on high level number 2. So that's our signal coming in from the radio. So I'm going to switch over to the linear impulse response, and then we're going to look at the transfer function engines and route the appropriate transfer function. So when we go into the measure settings here, you'll see this is the default setup. You have signal on your transfer function number 3, which is connected to microphones, and our internal loopback is connected to the reference of our transfer function engine number 3. We're going to leave that one alone. We're not changing that one. What we're going to do is we're going to use the open transfer function engine, which is TF number 6. And I know that there's 4 other open ones at the moment, but if we actually turn off the hardware multiplexing of Macs, you'll see that they quickly become populated. So when I say open, I just mean the always free transfer function engine number 6.
If I may jump in on that real quick,
please.
You could change any of these at any time, but what's nice about what Matt is suggesting is you don't ever have to worry about messing any of our default set stuff that's already set up in tune for controlling Macs. TF6 is never used by any of our default settings. So if you want to do any of these types of measurements, using TF6 is a really smart way of doing it, because if you ever, like Matt was just saying, switch out of multiplexing mode into discrete transfer function measurements, you could still use TF6. It doesn't change. Otherwise, you'd have to reroute and do all that other crazy stuff. So I really like what Matt shared as a pro tip, I guess you could call it. Use TF6 for any extra measurements you may be doing.
All right.
Are we ready to call him a pro yet?
Well,
I've seen it a couple times on YouTube. I don't know how that, what that counts for, but
University of YouTube.
Yeah. So, all right. So what we're going to do here, we're going to connect our TF6. We're going to connect the measure signal to high level input number 2, which is the one that has signal on it up above. And then for the reference input, we're going to connect that to our internal loopback. And then we're going to hit play. And what we're going to notice here is we have signal on the measure, but nothing on the reference. And that's because we didn't play the signal generator yet. So I'm going to go up here to the top right, or you can select it in the measure settings here. And I'm just going to hit play. Okay.
Show the measurement tab again real quick.
I will. Here's the measurement tab.
And go to the measurement setup.
Okay.
So now you'll see that there is a reference signal and there's a measure signal as well. And TF6, as Matt is showing right there, is playing and has signal on both the measure, which is the top bar, and the reference, which is the bottom bar. So we are good to go ahead and start looking at our data.
All right. So what we're seeing on the top screen is linear impulse response, and on the bottom is RTA. So I'm going to scale this graph out using these scale controls. And a little tip here, if you hover over the actual button, you'll see it tells you what it's going to do. So we're just going to return the graph to the default scale. And then I'm going to play my multi-mic on the bottom here. And let me make sure that we have signal coming in.
Multi-mic?
I'm sorry, not multi-mic. High level number 2.
There it goes.
All right. Let's see here. I think number 1 is actually what we're looking for. So let me change this transfer function back to number 1.
And I'll put you on zone 1.
All right. And
Damn.
there we go. All right. Sorry about that, everybody. So now on the bottom, you see the RTA signal from the high level input, which is coming out of the radio. And on the top, we see the impulse response of the time arriving to the high level input. So I'm going to zoom in here on the impulse and make sure that this is set properly. So we already have a reference delay set here. If I zero that out, this is what we would see. So when you look at the radio's time arrival, to make sense of phase, we have to set our reference delay. So when we look at the IR, we just have to zoom in a little further, and then we're going to right click right on the beginning of the impulse. So this is all noise here. And then right here is the beginning of the impulse right there. So we'll right click on that guy, or you can type it into the reference delay field. And now that we set the reference delay, phase will actually mean something.
So as a reminder on time-based measurements, phase is a time-based measurement, and as a pretty smart guy said once a long time ago, time is relative, so therefore phase is relative. By setting the reference delay, we're creating that relative measurement. So as Matt said, now the phase data actually makes sense because we know when the time is starting, and ultimately we know when things are arriving. So the phase plot that you see now looks different than it did a moment ago because we didn't have that reference. Without that reference delay, and once you get good at this, you can look at that and say, something's wrong. You see something like this, and you say, that makes sense. It's a nice, smooth, and continuous thing without a whole bunch of additional what's known as wraps or additional lines drawn on the screen as you see here. So,
yep. So having 0 in there obviously makes it very hard to see. So we're going to put our reference delay back in, and now what we're seeing is a couple of things. If we look at the RTA data, we see that it's pretty flat all the way down to about 60 hertz, and what we're seeing is the low pass or the high pass filter showing the phase shift in the phase domain. So this is phase shift due to the high pass filter. So it's undefeatable. We can't turn it off to show you the difference, but what I can do is raise it to show you what would happen. So I'm going to go ahead and raise the high pass filter on this radio here.
While he does that, I just want to point out that phase wrap like this and that the phase response looking the way it does isn't bad. It just is. It's just part of the measurement. And in fact, it's required in this case to get that roll off that we see as this high pass filter. So there may be opportunities to get filters that don't affect phase, but remember, phase is real. And if you measure a phase issue, if you have a filter that adjusts things and doesn't affect phase, you still have a problem. So you'd have to do something else in those cases, but that's another conversation. So.
Yeah. All right. So what I did here is I increased the high pass filter to 100 hertz, and I'm actually going to capture this by hitting the space bar. And we're just going to call this 100 hertz high pass filter. And now I'm going to turn it back off so we can see the difference. All right, so now it's off. And we can see what happened in the phase domain. Now, I didn't take a capture of the RTA. That's why we only see this one. So let me put that back on, and I'll take another capture of the RTA just so it makes it clear and distinct. So you have to select which graph you want to take a capture of before you capture it. And unless you're clicking the capture button to the right, that will work on whichever graph you choose.
The reason for that is time-based measurements are different than the standard measurements, like an RTA measurement, spectrum engine in that case. So the reason why you have to select it because it's capturing different bits of data. So RTA would be different. RTA and spectrograph would be different than magnitude, impulse response, phase. Now, here's the thing. When you take a phase capture like Matt did earlier, it's capturing all of the data for the time-based measurements. So you only have to do that once. So you could switch between magnitude, phase, impulse response, and you had that same data all across those time-based measurements.
So what you're saying
Well, it's also important to label your captures properly, because if you're in an RTA and you want to look up right speaker, it may be grayed out and you're like, oh, why can't I select it? Because it's probably a time-based measurement and not RTA. But if you labeled it properly or
You'd see
memorized
it in
the
the file.
extension,
Correct.
it'll be a lot.
Yeah, no one memorizes the extensions, especially these weird ones that we use.
So you can see here the difference between in the RTA as well as in phase graph. So like Steve said, if we switch to magnitude, we will also be able to see, I'm going to scroll down on the graph, we can see our previously captured data here. And that, I know they're both red, so I'm going to change the color of this one. So we're going to make this purple, right? So that goes just to prove that this purple trace is not the same data as the red trace. They're showing two different measurements. This measurement was captured via RTA. This one was captured via time transfer function, which is magnitude data, phase data. So now if we go back to phase, we see that purple data shows up. And if we also go to impulse response, we can see the purple data here. So,
and all we did was capture a phase trace.
Yep.
A quick question that did come in, Jeffrey Hald was asking, is this from a single input from the radio, or I'm assuming a single output of the radio, or is it a stereo signal?
So what we're doing is we're using the RCA outputs from Max to drive the input of the radio left and right. And on the output of the radio, we're currently only measuring one channel because we're only using the one input on Max. The what are we using? High input 2?
High input 1.
High input 1. We could switch it to high input 2, which we could connect to the other channel. So we're only measuring one channel at a time in this particular instance. But it's a good question, Jeff. And yes, you could do either one. So whatever you want.
And we'll get a little more into that in a little bit too. All right. So now we showed that. I also wanted to show what happens with equalization on the electrical measurement, and also show you some spectrograph stuff to see what to expect from the spectrograph and how you can use it as an installer tool when you're tuning a car and you hear some noise that you're like, that's, it's kind of piercing my ear. It's a little bright, but I don't know what frequency it is. Spectrograph can really help with that. So let me select the spectrograph here, and I'm going to select my input as high level 1.
Oh, it's so pretty.
All right. So now what I'm going to do here is I'm going to go into the radio and I'm going to add some EQ. And I'm going to have you guys guess what EQ I'm adding. This radio only has 3 simple EQ controls, by the way. So it's not really a trick question.
It's a good use of the spectrograph.
It is. I wish it was more prominent. Is there anything you could do to make the spectrograph stand out a little bit more?
That's a good question. So if we scale the RTA, now we have a lot more energy. So I'm going to turn the radio back down.
There should be good. So now you can see on a spectrograph, there was a boost applied somewhere. You could also see it in the RTA.
And if you didn't know, red means more energy.
Right. So basically what a spectrograph is doing, it's kind of looking down on the RTA response, if you can think of it that way. So normally you have a little line, right? So if you could like tip the line so that you could look down on it, things that are closer to you will show up as more intense colors. Things that are further away from you will show up as cooler colors or less. So you can see down on the left side of your graph, the blue that fades to black, that's the low frequency that corresponds to the roll-off at the low frequency end of things. And then through the rest of the response, it's green and pretty consistent as you go all the way across. And you'll notice in the RTA response, it's flat and relatively consistent as you go across until you get to around, what is that, around 3K, where it starts to rise up, and you'll see that it transitions from the green to the orange and then up to the red. And the red would be the most intense or the highest level of the RTA response. So you're kind of looking down on it in a way. And any changes that happen in the time domain, so to speak, as time is passing, in this case, time is passing from the bottom of the upper graph, scrolling up to the top. So the stuff that's at the top of the graph happened the longest time ago, and the stuff at the bottom of the graph happened more recently. Now, what can you use that for in terms of troubleshooting?
There's plenty of applications. I've used it myself in looking for noises in the system via electrical noise or
Door
mechanical
chimes.
noise. Sorry.
He said door chimes. And what's
chimes,
interesting about this is a lot of guys are probably thinking, well, I could probably see that on an RTA. Well, it depends on how fast your RTA is updating. If it's in a very rapid refresh rate, yes, you'll see the door chimes, but it'll be very hard to identify where that took place. So also, in those cases, your RTA is going to be moving a lot more as a more dynamic signal. So what you could do here is looking at the spectrograph, you'll see a burst of energy at whatever frequency that door chime was, and it'll pass in time. So you'll see how long it was, as well as what frequency it was. So you can actually see noise after it happened and not have to stare at your RTA. You can make the noise happen and then look at your screen. It's a really cool way of seeing what happened at some point in time when you weren't actually looking. That's how I use it anyway.
That's a really good way to use it. All right. So
I actually usually use it to, see the dynamics of thunder. See the frequency response of the thunder when it hits down here.
that's actually pretty cool.
It is pretty cool.
Things we use Max for. All right. So aside from the spectrograph, we're going to show you some other cool things and electrical measurements that you can take with Max. So what I want to show next, Steve, is I want to show looking at some speakers and taking impedance measurements.
A what?
That's what I said, impedance measurement.
What's an impedance measurement all about?
Where's Nick when you need him? No.
So just for those that may not understand what impedance is, when we talk about resistance, normally we're talking about things like this guy here, a resistor, just a basic thing that resists electricity. But most of the time we're talking about DC resistance. So when you hear the term resistance, it's usually something that's in DC, but speakers don't, well, hopefully they don't get a lot of DC. They have AC. And when you're looking at the resistance of AC, it's actually a little bit more complicated. And we kind of lump all the complications into one phrase called impedance. It's basically resistance and frequency plotted on a single graph. So what we're going to do is we're going to show you using Max how you can actually measure the impedance of a speaker using a basic probe, which, by the way, we do offer. So both from inventory. So, little probe kit here. And then we'll grab these guys
This is
out.
not a sales pitch.
No, not at all. You guys can make these. We actually have a help center article on how to make these on your own. So the impedance one is going to use this 1/4-inch jack, which you'll plug into the... On one side of Max, you'll have this, there we go, that guy there. And it's a monitor output or impedance measurement. So we'll take that and we'll jack it in there. On the other end, we have the business end is what I call it, where we can connect our probes. And we have other probes here that are a little bit easier to work with. And we're going to measure the impedance of this speaker. So Matt, you got all that stuff already set up instead of my props?
Yep. So first things first, on the tune screen here, I want to show you how to calibrate the impedance plot before you get started, because Max is really, really good, but to make it perfect, we just have to measure a resistor first and confirm that it's the right value. So what we're going to do here is Steve's got this little resistor in his hand.
It comes with the kit if you bought it from us. If not, you can grab any, at least somewhat decent resistor. Rob, do you mind showing?
There we go.
The little resistor. And what we'll do here is we'll grab just a multimeter, any old multimeter that you may have. So what Matt's going to do is he's going to measure this resistor. But I want to tell you something. You don't really need to worry about this, because most of the time when you're looking at impedance measurements, it doesn't matter the ultimate value. What you're looking at is a shape, and the shape is not going to change based on the resistor value. However, if you wanted to make comparison measurements and make them consistent from one measurement setting to another, using this resistor value, you can actually have the trace show you the real value of the impedance. So,
Can you hold that up for the camera, please?
I will try.
So we just have the Fluke multimeter set to resistance, right? Ohms, some people would call it.
Ohms.
First, I'm going to zero out the tips. I'll put them together. We should have 0. 0.1.
0.2.
0.1 we got down to, so we're pretty close. So now I'm going to connect these to this resistor here, and we got 10.3.
So call that 10.2, right? Because
Yep.
we had 0.1 before. So it's a 10.2 ohm actual value for that resistor.
So now that we know what that is, Steve's going to go ahead and connect that resistor to the probes that we have with these little Fluke clamps.
Cuban coffee is working.
All right, so now that we have that connected again, or whenever Steve's done.
Oh,
goofing
stop
off.
yelling at me. There we go. Now we got it.
All right, so now we're going to go back to the tune screen, Rob, if you don't mind.
There we go.
And I'm going to actually go into the measure settings again. We have to tell Max that we're about to connect to the impedance plug. So the input has to be switched using this Tf1 Impedance Mode. Anytime you're measuring impedance.
You're going fast here. So he went to the measure settings, to the measurement setup tab, and then he sees over on the right-hand side under the words transfer function, it's a Tf1 Impedance Mode, right? So what that's going to do is it's going to click that over and turn that on and watch what happens. So you'll see Tf1 now is set up to measure. What's shown on the graphic there was a little misleading. It's actually using the other side, the impedance probe measurement, but this is simply showing that there's an impedance setup on Max right now, ready to take measurements. So we can actually close out of this. We'll come back to this in a little bit.
All right. And now we need to play signal. All right. So right now we have pink noise playing, and we're going to go to our impedance here. And we want our number value of this trace. We want that to be right at 10.2 ohms. So right now you can see that it's right around 10.56. If you look at the very top of the screen, there's a value there where it says level. In the black box, it says 10.56. So what I'm going to do here is I'm going to hit the little impedance drop, the input drop down here. And we're going to go to the impedance numbers, and we're going to reduce this until we get it to the 10.2. So
It's scaled way in.
I'm gonna use the minus key to scale out a bit, and I'm gonna bring this down until it's at 10.2. So if I hit the shift key, I can do 0.01 intervals. So 10.25, and let's put the cursor over it. There we go, 10.2 ohm.
Perfect.
So we're at minus 0.3 is what we needed to get that to be perfect. So as we said before, Max is really, really close.
So we're going to take the resistor out, and now we can measure speakers. You got it?
We can?
We can.
Oh, okay. So we're just going to connect the probes to the speaker, positive to positive, negative to negative. Or if you're feeling like you want to do something different, go right ahead.
You may be able to hear the periodic pink noise coming through the speaker too.
So I'm actually going to change here into a different signal. I'm going to change it to a log suite. And we have these already saved.
Have to do that.
That's okay. So
These files were already created for you when you download Tune and have Max. It's already there for you.
All right. I'm going to make this screen a little bigger for us too.
Change the scale.
Yeah. Minus.
All right. So if you've ever seen an impedance curve, that's pretty classic right there. Now, the hard part is that the speaker is sitting right in front of us. So as we talk, it may affect it a little bit because there'll be vibrations in the air that'll possibly affect it.
So there's a couple things I want to do here. I want to capture this speaker and compare it to another speaker that we have next to it. See if they're the same. So this is a good way to test when you're working on speakers. If there's a defect with one of the speakers, you'll see it show up in the measurement. And we don't care necessarily exactly how it looks, just how it compares to the other speaker.
Right.
All right, so we're going to call this 6W3 number 1. You good?
That's cool. You got all those 6W3s laying around there.
Yeah, I got one other one here too. I don't know what to do with them.
I feel like they were supposed to go to someone.
So while Matt's there, I'll go ahead and make this connection on this guy. Positive and negative.
All right. So they are slightly different. Now, these are open box speakers that we don't know what they've been through.
It's pretty consistent, though.
It's pretty close. They're slightly different, but you can see that they're close enough. There's no big, massive defects in the driver. Now, what you would see if there was an issue in the driver is something more like this. And how's that happening right now, Steve?
I have my finger on the speaker.
You have your finger on the speaker? Oh, my goodness. So this actually brings us into our next point. which is, have you ever been working on a car and you're putting a grill or a door panel on top of the speaker and you're unsure if it's going to hit, if it's going to touch the speaker? And there's a bunch of different ways you can do this manually. Like you can take some clay and put it on top of the speaker with some tape and then put the panel on, see if it smushes it, right? But sometimes it's so close you couldn't even fit clay. So it's really tough in a lot of applications when you're working on cars to know if it's going to touch or not. Well, this makes it really easy because you can capture the trace before you put the panel on and then just put the panel on.
And then if you're doing it live like this, like let's just say the speaker's really close, right? So my hands are literally just in front of the speaker. And if you push on the door panel, you'll actually see it changing the impedance in real time. So you can say, oh, no, I got to change something because it's obviously going to hit. And obviously, as I talk and do all this other stuff, it makes it go crazy. But
yeah. And if you see, you might think, well, it's barely pushing on it. What's it really going to do to the speaker? You see that just a tiny little
thing. I'm looking for something, a little clippy thing here. If I did was I dropped a little twisty tie on it, and it made that kind of a change. Ready? I'll do it again.
Yeah, that's a big deal.
And it's nothing. It's,
right.
It's just a tiny little thing. In other words, impedance measurements are very detailed, very accurate, and can give you a really good indication if something's affecting the motion of a speaker as it's moving. And it's not just good for subwoofers. There's other things you could do. We're going to change this guy out, and I'm going to show you. A lot of people are going to be upset about seeing that. It's a C5 mid-range. Yes, we had one laying around. So we're going to connect this guy up. And logically, it's a smaller speaker. So what you're looking at with the peaks on the impedance plot there is the resonance of the driver effectively. So this one has a higher resonance because as it's normal anyway for a smaller speaker to have a higher resonance point. So you can see that compared to the other one. Here again, light taps on the speaker cone will cause changes that are pretty dramatic on the speaker.
Try your twisty tie again.
Let's see. Okay, here's my twisty.
Well, just sit it on top. I think on this speaker, you'll see a pretty big difference. Mm-hmm. Yeah, there you go. You can see it's crushing the top point of the driver.
Well, crushing's a bit extreme, right? So it's just sitting on there. So did they get it, Rob?
No, you were too fast.
Yeah, I'll do it again.
Yeah, there we go.
Yeah,
you can see a little twisty tie on there.
Yeah.
Okay.
Pull that guy off. There we go. Okay, so that's impedance measurements. You have anything else to share on that?
What else can you do with impedance measurements?
One thing I like to share with people, and we don't have time to get into all the details of this, but if you have a sealed enclosure with a subwoofer in it, if you want to check the resonance of the sealed box, it's no longer just the driver, it's the whole system. So you can take your impedance probe measurement at the terminal of the entire enclosure, and you can see the resonance of it. Similarly, if you have a ported enclosure, you can not only see the resonance of the box in that case, but you'll see the tuning frequency. Those impedance plots, as you go from low frequency to high frequency, you'll see a peak, then they'll come down, you'll see a valley and another peak, and then they'll taper down and do some other stuff at the top end. Between those two peaks, the valley there, the lowest point of the valley, that's your tuning frequency. So if you want to find out the true tuning frequency of a box, instead of doing it the old-fashioned way of watching the cone to see where it moves the least, you can now actually do an impedance measurement and get a really accurate value of what that tuning frequency really is. Pretty cool. Pretty cool, and it all comes with it, other than the probe. So,
yeah.
All right, what else we got, Matt?
All right, so I think we're done with impedance stuff for now. Next, I'd like to get into a little bit of OEM integration. And This is a problem that we run into a lot. People ask us, what do you do in applications where you don't have a way to inject signal into a radio? You have a car, you have no aux input.
Can't do anything. You're done.
Done? You got to send the car somewhere else.
No.
So we're going to do a little bit of OEM integration with a radio that you guys might know has a pretty big following because it is known to have all pass filters on the channels. It's a Toyota Tacoma radio. This one's from a 2018 specifically. And what we're going to do here is this radio does not have an auxiliary input. It does not have a USB that we can use. We're using a CD, literally a CD. Did you guys hear that? A CD.
Does anyone know what a CD is anymore? So that's what we're working with right there. Matt was able to procure this from a very, very friendly and helpful local dealer. Thank you, Zach. So we actually, it was quite an ordeal here for a while there, trying to get the periodic pink noise onto a CD because we had to find one. Anyway, we got it. So what you're going to look at is the output of this radio. I think, Matt, you're going to do left and then you're going to show right.
Yeah, we can do that. And then we can look at both channels individually and see what happens when you sum them.
Does that have an EQ, by the way?
This does have an EQ.
Fantastic. Yes. There was a question that showed up, and we'll address it later. Someone asked about door chime stuff, so we'll come back to that. I saw the question in there. Jeff asked it, so we'll come back to that, Jeff.
Actually, before Matt gets going with his measurements, I'll get on my soapbox for a second here. Matt talked about a scenario of integration where, maybe you don't have an aux. Obviously, we need to have a proper signal when we get into the acoustical side of measuring. We need that reference, right? Flat, full range, time coherence, so we can analyze phase, get our IRs set up. But for any integration in general, whether you're figuring out if you need a fix 82 or fix 86 or a preamp processor, these are the steps that we've been preaching for years, except sometimes you would need either an expensive standalone RTA or an expensive oscilloscope. You need to know the output voltage of the amplifier or source unit. What's the pass band? Are they band restricted channels where you have a high pass for tweeters, band pass for mid-range, mid-bass? What's the frequency response? Is there any equalization? Is it fixed or dynamic? These are all important aspects that need to be known, and in a perfect world, known before you get into the installation.
That'd be really nice, yeah.
Yeah. But I know you got to take the car apart. But for a retail perspective, knowing what parts you need to properly integrate, if needed, is the key. Because if we screw up the signal upstream, it's going to make it that much harder downstream when we're taking acoustical measurements and adjusting the DSP to make it sound the way that it should. So, for integration in general, even if you're not, needing a reference signal for phase-based acoustic measurements, it should be a must for every install. And that's something, we've been preaching for years. And, just with Max, it's another cool way to do it. You can get captures. I would say even screen capture, screen print, print out, whatever, and give it to the customer if you're a retailer. Here's what your signal was. Here's what the Fix 82 did to fix it, so we had the right signal to work with. OEM integration can be weird because some of the processors can be a little pricey. And as for a consumer, well, why am I paying for that?
You have to justify
give them that value with the printouts and the screenshots that you can take with Max. And you're getting accurate measurements, which will help you pick the right products off a soapbox.
There you go. Thank you for that, though.
I couldn't have said it better myself.
No, without a doubt. It's there needs to be some kind of sensible way of doing that, and I think we have it now. So what Rob was just sharing with us, it's a great segue, by the way, Rob. So even though it was a soapbox, and we're cool with that, there's a good jumping point because we have this radio now, and Matt's going to show us how to do a lot of the measurements that you just talked about. So take it away. Go,
right,
baby,
back
go.
On it. All right. So what we have here, like Steve said, we have a CD. In the CD drive, we actually burn periodic pink noise onto the CD. And you might ask, why periodic pink noise? Because the periodic pink noise actually has a beginning and an end. It's a period, right? So when you listen to it, it kind of has like a clicking sound as you're listening to it.
As it restarts.
So every time that the signal restarts, that's something that we can potentially, grab that information and use that as the beginning of our measurement. So we don't have a way to inject signal via auxiliary input because we don't have an auxiliary input jack on this radio. We can't go through Bluetooth. So we had to use CD. So what we're going to do here is we're going to go into our measure settings again. And I'm going to go to the measurement setup and we are going to turn off impedance mode. All right. So now we have high level input on 1 and 2. What we're seeing here is the left channel of the radio and the right channel of the radio. So we're going to connect, we're only going to look at one channel at a time. So we're going to connect our TF6 measure to high level 1. It's already there, so we don't have to change it. And our reference signal is going to be our internal loopback. So we're good there too. We don't have to change any of that. What we do need to change is our stimulus. So I'm going to go back to the signal gen, and I do have a file that we used for this, which is the, in my downloads folder for 1 second, pink periodic noise. Okay, and I'm going to go ahead and hit play on that. So this noise that we're using is the same noise that we burned at the CD. So it's the same reference signal.
The same file. We made
Right,
the
same
file,
file.
we put it in the folder, then we burned it to a disk. So now we're using the file as the reference signal, and it's going to be played from the CD through the source unit to the output wires, which he's used the little probe thing that we have here, using high level in 1, I think, right?
High level in 1 is on the left channel.
Right.
High level in 2 is on the right channel.
Perfect. Okay, so we have two of them, one on the left, one on the right, and that's going to show us both. What are we looking at there, Matt? What is that?
So this is high level input 1. So this is the left channel looking at the RTA graph. And you guys all know what an RTA is by now. At least I hope you do if you've been paying attention to our trainings. So on the bottom of the screen, you have frequency response, and on the side, you have amplitude, right? So this is left side. Now I'm going to play high level input number 2, which is the right side. Okay. So there are some differences between the two channels in equalization, like this hump here, that's a little bit different, and some little differences at the top end here. But what you see here are these massive nulls in the middle. And what is that, Steve?
It's a, I don't know.
I'm going to guess an all-pass filter.
Well, is there a way we can look at that? Well, there is.
So remember, all pass filter, that's a time-based thing. That's a phase EQ. So would we see it in a single channel RTA?
No, I don't think we could see it in a single channel.
No.
What if we sum the channels together and then look at the result? If we're just going to see a bigger notch, right?
Potentially, yeah.
If there's all pass filters there. So how can we see it in real time without guessing?
Well, if you had a way of doing a reference for the time, you could look at phase.
All right. Well, the easy way would be have an aux into the radio. If you have an aux into the radio, you
Then
can
you're
absolutely
done, right?
look at phase very simply, right? But the way we did it today is not too difficult either. So there's 3 ways that you can do this. You can put it on a CD like we did, right? Well, there's probably more than 3 ways. Put it on a CD. You can Bluetooth to the radio from your phone, but you need the periodic pink noise. It has to be that. The third way would be a USB with USB, with periodic pink noise on a USB stick. Another way, you could do it over FM modulation, broadcast it, but that's kind of getting into the weeds. So what we're going to do here is we're going to pull up the impulse response, right? And you guys know what that is now because we've been talking about it for weeks. So we want to look at the impulse response of transfer function number 6. Remember, this is our left channel and our reference, right? Now, the problem is our reference is not the same. Even though it's the same signal, they're coming from 2 different places. So if you look closely, you'll see our impulse response is actually moving. It's literally moving in time. So let me zoom in on this so we can get a better look.
See how it's kind of wiggling and shifting a little bit back and forth and pulsing?
So now,
I think did you engage it already?
well, no, this is from earlier. Let me take that out. Sorry. So what's happening? I'm just going to right click on the beginning of this as my reference, right? And let me rescale again and watch what happens when I set that as my reference. It's already moving. It's no longer the reference, right? And that's what would happen when you use Bluetooth or use CD or anything else. That's the problem. You can't use this for analyzing channels against each other because it's moving in real time.
You see how he can see that, though. If you just look at the tallest spike, slowly but surely it is moving towards the left side of the screen. Where the solid line is, if you move there, where the plus thing is right now, that's where it started. So as time is passing, it's moving further to the left, which means it's showing up earlier and earlier and earlier, which is just bizarre. And it's because of the 2 different sources of where the signal is coming from versus where we're measuring it. Is there anything you could do to stop that? It's annoying.
Well, there's these guys. They made this really cool program. It's called Tune4. Let me tell you a little bit about it. So if you go up here to the true delay finder and you select the true delay words,
Hover over it.
we can actually see. I'm going to hover over this first so it shows up. Right. So this tells us the command, how to actually do these commands. But these commands are listed right here. So
no one can read that. You're going to have to.
I'm going to read it. I'm going to read it. So what we're going to do here is we're going to track the peak delay. So what happens is it attempts to track a changing impulse response time by monitoring the peak amplitude value. So this is very useful for what we're doing. So I'm going to, again, hover over it to see what we got to do.
So some key words about that. It's going to attempt to do this. Sometimes it may not work, but most of the times it will. So go ahead, Matt.
Good call there. So we're going to do Command plus Shift on the delay finder. Okay. So I'm going to hover over the delay finder. I'm going to hit Command Shift and click.
We are on a Mac, by the way.
And it says all outputs are muted. That's okay. We don't care about that. So now it moved the beginning peak of the impulse response to 3658. And if you look at the value, the numbers here, you'll see it's constantly changing.
And you'll also notice the graph kind of shakes a little bit because it's constantly updating to put that 0 reference back where the peak is. So we're tracking the peak delay. So by the definition, it's forcing it back every single time it changes. It's shoving it right back to the 0 point. So that little flicker, while annoying, is good for us because now we can actually see some type of time-based measurements by using this delay tracking. Is that right?
That sounds right to me. I'm just blown away how cool this is every time I see
know.
it.
It's really neat.
All right, so now that we have a reference delay, that's we have a reference that's relative to this point in time that's actively changing, we can look at phase. And what do we see when we rescale this phase graph? We see an all-pass filter.
How do you know?
Because there's a break in the wraps.
So what's happening is the phase response starts in the upper left-hand corner and comes down pretty consistently down, and then it suddenly drops off the bottom of the screen, and then it wraps to the top. That's what Matt's referring to with a wrap, and then it continues on its merry way down the other side. That type of behavior is indicative of an all-pass filter or a high or low-pass filter. But in this case, we know that's not the case because the RTA is showing, although it's not pretty, it's a relatively full-range response. And in that region, if it was a high-pass filter, the lows would disappear entirely. If it was a low-pass filter, the highs would disappear entirely. In this case, neither of those things is happening. So the only thing that could logically cause this type of additional wrap would be an all-pass filter. So you can actually see that behavior by using delay tracking.
I'm going to just show here really quickly what a target looks like with the see, look, our delay tracking gave up for a second there. Don't mind it. Let me get back to it. Yeah, see, we lost it. So we're going to do the same thing we did before. We're going to do Command Shift click. All right, now we're back on it. So looking at this here, when we compare the red trace right in the center of the graph, that's a target. And what I'm going to do to that target, I'm going to add an all-pass filter so you can see what happens. That's our current tweeter target.
So you pulled it away from the front of the Z order.
Before I switch, just so you guys know, the value of this all-pass filter is going to be at 448. Okay, so I'm going to turn on an all-pass filter at 448 on this channel. 448, Q of 5 likely, right? So now let me go back and reset our reference delay.
So what's happening there is when you're the delay tracking looks at the data that's at the front of the Z order, and the Z order is like front to back, right? Mm-hmm. So you have X along the horizontal, Y along the vertical, and then the Z is front to back. So right now the
layers,
it's like layers. Yeah, it's I'm old. We used to have the overhead projector, and you could put different overheads on top, right? This is the stacking of those overhead projections, basically. So the purple trace is currently in the front, and that's the one where the delay tracking is going to try to lock onto. When that becomes not in the front, that delay tracking breaks and goes away. That's why it keeps drifting on us.
Yep. So what you see here is that all-pass filter I put in on the target, the red trace, which is in the back, 448 hertz, and it's a Q of roughly about 5. And there's a little bit of EQ around it, but you can see that there is indeed an all-pass filter. That's the frequency it's at. And in order to fix this, you would have to put an appropriate all-pass filter that matches it on the other channel. Because if there's already an all-pass filter, you can't take it away. Don't try it. It doesn't work. So now, Steve, we're going to look at the other channel. So what I'm going to do here, I'm going to capture this one. Okay, so I'm going to hit the space bar, and I'm going to call this left channel. We'll call it that. I should have said left channel phase.
Rob is upset with you.
I know. So now I'm going to capture the same thing on my graph on the bottom. So this is left channel RTA. Okay. And the right channel is already playing down here. That's high level number 2.
Right.
And I'm going to go back to my measure settings here, and I'm just going to change my input for the measure for transfer function engine number 6. I'm going to change that to number 2. Okay, so now
So we went from the left channel to the right channel, essentially.
correct, left channel to right channel. So now we have to go back to our impulse response and double check that it's holding. So it looks like, yes, we're still tracking the peak, so no issues there. So let's go back to phase, and what do we see here? Let me get this red trace out of the way.
Whoa, whoa.
What is that?
Looks like an all-pass filter, man.
Another one?
Apparently, it does have an all-pass filter on both channels, but they're at different frequencies.
Huh. What do you know? Why is Toyota doing this to us?
Because they like all-pass filters, apparently.
I guess so. So, as Steve mentioned, what you're seeing here is you're seeing a second all-pass filter on the other channel. So I'm going to capture this one and call this the right channel phase this time. Right channel phase. So the question here is, what can we do to fix this? Because there's a couple options, right? A couple different things we could do. But Steve, what do you think we could do to fix this?
Well, one logical thing would be put an all-pass filter on the opposite channel, but in this case, it would be on each channel at different frequencies. Would that help us?
It likely would, actually. Although it sounds silly, putting the equal all-pass filter on the other channel would indeed create the same wrap. So just so you know, it doesn't matter how many wraps are on a given channel, right? So let me bring up the tweeter channel, for example. When I click on this tweeter channel and I start adding delay, that's all right. When I start adding delay, you see there's more wraps. The wraps are relative to the other drivers.
Correct.
So as long as the other drivers have the same amount of wraps, it doesn't matter. Obviously, more wraps make it a little harder to see the data. But with that being said, if we added 2 all-pass filters, one on the left side, one on the right, to match the opposite so that the phase response was even for both channels, you would be able to get a good signal out of the radio, relatively good, as good as you're going to get out of a factory Toyota deck. So that's one thing. What's another thing we can do to fix the all-pass filters?
Turn them off.
we could take the radio out and put a new one in. That's super easy. Pull the radio, do something different. Another option would be you could do a 2-channel input directly to the amplifier, bypassing the factory radio. So if you go with just a headphone jack or a Bluetooth, and you want to plug into your phone and go straight into the amplifier, that's an option.
I would actually contend that, looking at these electrical outputs from this radio, this is going to go into some type of amplifier or possibly another processor. The assumption here is that since we're talking about time-based measurements, you'll probably have some kind of a DSP so that you could do an all-pass if you chose to. But I wonder, I see some comments kind of crabbing on Toyota, and it may be justified, but there may be a reason why they did that. Yeah. So if you're using the same locations that factory did, and you see this all-pass behavior, there may be a good reason for it. Because remember, it's not affecting frequency response, it's only affecting the time domain. So if there's an all-pass filter put on one channel or another or both, it may be to improve the time-based measurements in the actual vehicle using those locations. So if you're using those locations, I wouldn't go crazy just looking at the electrical response. I'd make a note of it and say, I saw that there was an all-pass on both channels in this case. Let's see what happens when I pass it through my entire system, through my audio system, through the speakers, and then capture it by a time-based microphone. And then look at the phase differences between left and right and see if there's any need to do any of that. In other words, don't sweat it yet. It's not that bad, and there's a potential way of fixing it anyway. But if there's not, like Matt said, your only option then would be to bypass it because there is no off button on it. We wish there were, but there isn't. So in this case, we don't have an easy way of doing this for our conversation today, but we wanted to show you using the electrical measuring capability of Tune 4 and Max that you can actually see the exact position and the shape of an all-pass filter on both channels in this case at the same, roughly at the same time. Capture the data and compare left to right, and you can see exactly what's going on in the electrical domain, which is really cool.
Yep,
really cool.
The all-pass filters from the factory are interesting, especially on a base radio like the Tacoma there. But from my experience, when they put those in the cars, it definitely helps with the imaging by having essentially, a phase shift within certain frequencies. Say what you will, they've spent tons of money and they've got very talented engineers designing the audio systems, and it may not be at the level we like, and of course there's a cost to it. I get it, but the guys that are designing these systems, they're not just saying, "Oh, I'm going to throw an all pass filter at 352 hertz for the heck of it,"
to screw up the aftermarket guys.
They're
right?
listening, their measurements, seeing an improvement in the cabin, and typically it'll be for imaging or something all the time, phase like Steve was talking about, to help get a little more, out of it.
Right. Rob brings up a really good point. The OEM may or may not be out to get us. We're not entirely sure of that, but let's give them the benefit of the doubt that they're looking to create a positive experience for their customers, just like we would try to do for any of our customers, give them a positive experience. Imagine if you were tuning a system and you wound up putting an all-pass filter to improve the staging and imaging, like Rob just said, to make sure that things lined up in time. If you did that and your customer saw what you did, it's okay because it was for their benefit. So I'm pretty sure, I'd like to think that Toyota does this as a way of improving the system that they are selling. And it only messes up us because we're trying to improve upon that, which is usually fairly easy to do in terms of drivers and things of that nature. But when it comes to the time-based measurements, one struggle that we've had, and we've had all kinds of workarounds before that allows us to get some kind of visibility, but most of them are what I call manipulating the wrong stuff. So you're looking at frequency and level to determine what's going on in the time domain. And it just doesn't make a lot of sense to me, but it's hard to do it any other way until you have a system like this where you can actually track that peak delay. And it's not perfect every time, as you saw. You have to kind of work with it a little bit. But once you get that, you wind up with rock solid phase measurements, and you can actually see the exact location and shape of the phase difference and see that all pass behavior. Knowing exactly what's going on allows you to be much more precise with your solution should you need one. So, very, very cool.
Now, to add to that, when you get to this point, and you now know there's an all-pass filter on each channel, right? And you want to take it further, you wouldn't necessarily, like Steve and Rob said, you don't want to mess with it yet. Wait until you get to the acoustic domain where you're measuring it with a microphone, because that's where we have the all-pass filter that can align to make these match. So don't worry about it on the input stages. Wait till you get to the output stages. I agree with that. It's going to look slightly different when you get to the acoustic side, because you're going to have more wraps. There's more things happening in that range because of the delay, right? You have more delay, the time of flight. It's going to add wraps to this. And that's okay. You just need to be able to look through the data and determine where the all-pass filters are, which you can do with Max.
Earlier we kind of made a comment, I guess it was sort of funny, that there is no magic in the box anymore. You could see what's going on in all three dimensions. On the bottom graph here, you can see level and frequency response, and on the top, you can see the time response or the phase response. You can see exactly what's going on with individual signals from any system you're likely to encounter. So one thing that we didn't really talk much about was the electrical input capability on a Max box on these XLR inputs that we're using to take these measurements. It's an 80 volt peak. Not peak to peak, 8 volts peak. So it would be 160 volts peak to peak. We did this because we wanted you guys to be able to measure the output of virtually any amplifier that you're likely to encounter for almost any application that you're probably ever going to see. Now, there may be some outliers that are, a couple of thousand watts of power that you may not be able to measure at full tilt boogie. It's a technical term. But you may not be able to get the full level out of it, but up to 160 volts peak to peak, you can measure directly into a single input on Max using the XLR inputs.
You're telling me I can measure 1500?
Yes, you can measure the output of an RT 1500, a 1500 watt amplifier using the inputs on Max.
There you go, Glenn. That's another challenge for you.
No, don't challenge him. He finds a way of doing everything. So,
one other thing I wanted to add. Can you bring up the tune screen? Thanks, Rob. There's only one way to determine where these all-pass filters are, and that's to look at phase. There's other methods that can tell you if there's an issue. Like if you were to sum these two signals together and then feed it into an RTA, you'll see there's a big dip there, a big null caused by the two individual all-pass filters. But you'll never know what frequency they're at. You'll never know how to fix them. So in those applications, your only option is to bypass it, or it's going to sound bad. So that's
Think about what would happen if we took the left and right signals, summed them together, and saw what would happen. We would say, there must be an all pass on that. And we put it all pass. We wouldn't know what frequency necessarily. We kind of see where the dip is. So we put it at that frequency. And what we would see is suddenly at that frequency, it'd be good. But at the other frequency, it wouldn't be. Because you didn't know there was another one on the other channel. You're only seeing the result of both of them together. So it's you're kind of chasing your tail a little bit. So you change the all pass to the other frequency. Now you still have the other problem. So which one do you put on which channel? This allows you to see exactly which one to put on which channel. You see on, if you put the screen back up, you put one on the purple, the wrap that's on the purple, you put that all pass on the yellow. And the one that's on the yellow, you put that all pass on the purple. So you're counteracting what's happening on both channels. And we have no way of easily doing that right now because we're not actually in a real situation. We're just sitting on my desk. But you'd be able to see the result if you needed it. And this is all in the electrical domain, mind you. So.
It's still like, as I'm staring at the screen, it still just blows me away. Like for so many years, we had to guess,
right?
Like you said, you don't know if there's something on the other one. If and looking at the RTA and seeing we have a, full range or close enough to full range signal, as we've talked about in the past, when we talk about phase, you'll see the phase wrap happens where the low pass filter is set, where a high pass filter is set. And you can see that in the RTA. If you see a wrap in a full range signal, it is most likely going to be an all pass filter. And without a doubt, that is the easiest way to identify it. And we've never had, there were, if you had super expensive test equipment, like our engineers have maybe, but
even there, it was a challenge.
Yeah, but for like a retailer in the shop trying to figure out how to properly integrate or tune a car, this is without a doubt the easiest way and most visible way to precisely know where not just the all-pass filter is set, but then we can start to see, the width of it, get ideas for cues to make adjustments. It's all in front of us now. There is no more guessing. There's no more throwing stuff at a wall and hoping it sticks. It is visible, and data doesn't lie. This is a pure electrical measurement from the source.
Excellent points, Rob, all of them. So I was just showing Matt some of the chats that we had, messages in the chat. Jeff was asking about simulating a door chime. By the way, let me just double check my notes here. I think we covered all of it. Yes, we did. So so what he's going to do now is we've got actually. You want to put the RTA on there too, just to see both? Sure. So what we're going to do is we're going to answer Jeff Hall's question from earlier, the simulating the door chime for the audience. And it's a really good point, Jeff. And if I had seen it earlier, I would have jumped on that right away for it. So we're using this radio here, and it does have an EQ, and hopefully we could make the change relatively quickly. So you're looking at the top is the RTA, and the bottom is the spectrograph. And I think Sean made a comment that it's like a log of RTA. And that's a pretty good way of calling it. It's like what happened during that RTA measurement. So you see where it's white on that screen right now? We peaked out. We got it really loud at that point. So there he peaked it out, and then it comes back down.
White hot.
Up and down. So you can actually see that's like what a door chime might look like, right?
Wouldn't be as wide, but
if he stops, right? Once the RTA stabilizes, you would have no idea where that tone was unless you happen to be looking at the screen when it was happening. But that's hard sometimes when you're actually in a car hooking up wires and making connections to keep looking back at the screen. In this case, we could see right around 1500 hertz, it was pulsing, doing something repeatedly. And we could assume at that point that was the door chime. But in this case, obviously, it was simulation, as Jeff suggested we do. But you can kind of see what happened as a log, like Sean was saying, over time. It's not a time-based measurement. It's simply a recorded history of what happened to your RTA over time. So.
To add to that, it's very important distinction that Steve didn't make clear earlier. He told me, but not to everybody. You have to make sure that your data is scaled on the graph to get meaningful spectrograph data. So like right now, there's still stuff happening, but we're scaled out so far that it looks like all the energy is good. If I use the auto scale y-axis right here and I just select that, you can see the nulls are blue and the peaks are red. And then again, I'll turn the mid-range up, and there's our white. So it's very important that you scale the spectrograph, or you're going to be smashing your head against the wall wondering why nothing's working. You have to get the graph to a scale that makes sense for the spectrograph. So what other questions did we have? I did want to make one correction, actually. I think Andy said earlier that the radio was a JBL OEM radio. This is a non-JBL radio. So just to be clear, I don't know if the JBL radios do have it, but I know the non-amplified JBL radios do have it. So that's what this is.
Yeah, that's what's interesting is a base system with no amplifier, yet they still have a DSP chip in there to do those all-pass filters.
Well, some of those chips, at least at one point, got pretty inexpensive, especially when you're buying the quantity that Toyota can buy.
Yes.
Right? It's, we're
last
talking,
2 years have changed that just a smidge.
just a little bit, yeah. That's why the qualifier traditionally in the past, those chips, and they're not DSP chips like the ones that all of us are familiar with, ones that we could program and change and modify and all that. What these are that I call them burned chips. So they program the chip to do a specific thing, and they make a whole bunch of those. Yep. And Toyota's the reason why we all say, "Oh yeah, that's a Toyota," because you've seen it a bunch of times because they're all over the place. Companies like JL Audio and other companies that make DSPs, we're buying a much smaller number of these DSPs, but we also have a different application in mind. We're trying to do a multitude of things, allowing flexibility and adjustability. So the chips that we are using are going to be different and definitely more expensive. One, because of the flexibility, and two, because of the quantity. So, yeah. What else we got?
All right. So I know this was kind of addressed when we talked about using reference signal if the vehicle does not have an aux input, but Israel was asking, can he trust Bluetooth signals playing pink noise?
Okay. So with Bluetooth, you can absolutely use that for pink noise, for RTA. That's no problem, as long as the Bluetooth will play all the way up to 20K, and you'll find that sometimes they don't. So you have to look at the RTA graph and see what's happening on your Bluetooth to make sure that it's not rolling off at the top end, because if it is, you're going to have to find another way to inject signal. As far as
make sure it's not a compressed file that you're playing as well, because then you can lose some top end and bottom end.
If I may just jump in on that, excellent points, one and all. If you take the file that's recorded, that's a full range signal, and you put it onto the thumb drive, if you create that and then play it back over Bluetooth, if it looks significantly different at the top end, there's something that's affecting that signal. And it's possibly the Bluetooth, it possibly is compression, but it's something that's different than what it was originally. And by identifying that, at least right? So if you're trying to fix issues with high frequency roll off, it may not actually be real. It may be the playback mechanism of the Bluetooth. So in that regard, you may not be able to trust it, but at least you can see it now. So,
okay. And then as far as time-related signals through Bluetooth, you could do what we just did with the CD. You could play periodic pink noise over Bluetooth and track the peak. But that will not work for system tuning. That is only for identifying a single channel, looking at what's happening on that channel to make sure there's no all-pass filters. It's not going to tell you relative delay, how that compares to another channel. So it's good for some things, but Bluetooth is definitely not the ideal method when there's other options available.
I think, you have typically there's varying latency with Bluetooth. And if you're taking time-based measurements where you need a solid reference and a solid measurement, Bluetooth, it's kind of moving all over the place in time. So you're never going to have that accuracy.
It does its own thing, and it's not going to be in sync with anything you're likely to use. So like Matt said, for troubleshooting and determining the basic phase response of an individual channel, you can do that. But doing comparative stuff, once you're doing system tuning, you just can't.
There's other ways to do system tuning without an aux-in, and we'll definitely get into that into a future session. Talk about how we can measure a radio and tune a system without a reference input, but that will be another session for sure.
Today was about taking all electrical measurements with Max, and I think we've covered quite a bit of ground. Rob, is there anything that we missed?
Well, there's a question not related to our topic today, but I thought it was a good one from Andy. He was asking what made JL Audio design regulated amplifiers, which would be with our RIPS technology, first found on Slash, all the variations of Slash, and of course now on the HD and MHD amplifiers.
put his comment back up. I accidentally clicked. So the funny answer would be, because we like to do things the hard way, the long and short of it is this, that one of our engineers, Bruce McMillan, is a mastermind when it comes to regulated power supply amplifiers. So I think the real question is, why did we choose to go down that path? We chose to go down that path because a regulated power supply amplifier is going to be very consistent in its power delivery. So in any application where you're dealing with an electrical system, particularly in a car or in a boat, there's going to be fluctuations in the electrical supply to an amplifier. Most amplifiers are what's known as non-regulated. And what that means is that as the supply voltage very rarely increases, but as it fluctuates, the power output potential of that amplifier will fluctuate with it. One changes, the other one changes with it. What a regulated power supply amplifier does is, regardless of what's happening on the supply side, the power output remains very, very consistent. And it's rock solid in most cases, unless you do something completely ridiculous with the supply side. Mm-hmm. And then the amplifier will shut off. So it goes from full power to zero. Right? So that'd be a fluctuation. And so I guess then the question would be, so why is that important? If you're looking for what I think is the ultimate in fidelity, where you want consistent delivery without any distortion being injected into the system as a result of the supply fluctuation, regulated power supplies all day long. Mm-hmm. Now, this cool technology has two main drawbacks that make most people stay away from it. And I'm going to be honest with you about this. The first one is it's really expensive to do it right. Our guy BMAC is really good at this, and he has a really great design, but there's additional components required to make a regulated power supply amplifier. It's not that easy, so it winds up being more expensive. And the other side of it is, in certain applications where your supply voltage is not stable, by drawing extra, because there is no free lunch. So pause for a moment, collect my breath. Ohm's law. No, I'm not going to get into it. But one aspect of it is, to make power in watts, you need voltage and current. Mm-hmm. If the power in watts is relatively consistent and voltage drops on the supply side, the current has to go up. Just has to. There's no way around that. If supply voltage drops, current has to go up to maintain power in the output. If you're dealing with an electrical system that cannot feed the beast, that cannot provide enough current, you will wind up with voltage drops that could be significant, and it could cause either electrical problems in the car or for the amplifier to actually shut down. Mm-hmm. So if you cannot feed the beast, I would actually recommend staying away from a regulated amplifier. And in a lot of boats, we tell people not to go too crazy on regulated amplifiers because of that exact issue. Look, here's the thing. If you're driving a Honda Civic and you got regulated power supplies at really big amplifiers, if you wind up with a problem down the road, you call your buddy, hey, I got a problem. Can you come help me out? If you're out on the open water and you got a problem with your electrical system, CTO is very expensive. They are not your friend. So the long and short of it is, if you have a way of feeding the beast and you can afford a regulated power supply amplifier, it can deliver excellent fidelity. And that's why we chose to do it. And we still make them. Obviously, our HD amplifiers are regulated power supply amplifiers, and our MHD are regulated power supply amplifiers. But the vast majority of amps that you're likely to use, including from JL Audio, like our VXI and MVI and all the others, will be non-regulated power supplies. And there you go. Hopefully that answered it. I know there's a long answer to a really short question.
Did you practice for that question up front?
Well, the funny thing that where Matt's going with that is, as a company, JL Audio tends to take the harder approach when we feel that there's a reason for it. Yeah. This goes back to the early days of the company when we had our reference manual. Most companies would make a subwoofer and say, put it in this box and have at it. We actually gave a range of enclosure options, ported and sealed, and different size boxes and different tuning frequencies, so that you could dial it in and make sense for a given application. Now, that required additional education and a lot more support. But hey, it kept me in a job, right?
Yeah.
but the benefit was real.
Complex boxes when it makes sense.
So there you go.
Great.
What else we got? Anything?
No, that was pretty much it. Zach said you're welcome for the source unit. And random W7 post.
You got to get one of those. And
go W7. No one asking for 15 W7s. That's been a while.
Which one?
More along the lines for staging, meshing, crossovers by Andy.
So Andy had a question. I'm going to put it up there so you don't have to scroll for it. I'm not entirely sure what he means. So this is more along the lines of staging.
So when this question came up is when we were looking at It was before the all pass filters. It was in the electrical measurements that we were taking. I think it was when you had the high pass filter on and was moving it around and stuff early on.
So I'm going to take some guesses as to what he's talking about. Meshing crossovers and phase alignments. So that was probably when you were showing how to identify all pass behavior.
No, I think this was beginning. This was 415.
It would have been before. It was when we first had like a high pass.
This might have been looking at the radio. Andy, if you're still here, can you maybe clarify that for us?
Yeah, don't want to leave it unanswered if we could help.
We'll give you about a minute.
Countdown now.
I'd play a song, but I don't want copyright violations again. Who would have thought that one time Kevin playing the Jeopardy song for 10 seconds would get pinged for a copyright?
Unreal.
That was while we wait to see if anything comes in from Andy. That was a really cool session and kind of neat to see Max and Tune 4 being used outside of the acoustical domain, which is all we've really talked about with it, but it's really starting to get into the electrical side and how it's not just, I mean, it's a measurement device, yes, but it's not just an RTA or for system tuning, but it really is a tool that can be used for troubleshooting, finding out what's on the wires to choose the right equipment. There's so many things that you can do with Max. It's just, it blows me away every time we kind of unravel or peel back more of the onion and see what it can really do.
Well, a lot of people have asked us how come there's like no manual on how to use it, and the reality is it's just massive. There's just so many different things, and we are working on additional training support to kind of cover. Just learning where all the controls are. That's a session, right? Then learning what those controls actually do for you is another session, and then how to interpret that data is yet another session, and then making use of all that information in a meaningful way, that's another session. So there's a lot of content to cover, and we're going to get there eventually. It's just we want to structure it in such a way that people can follow along, and who knows, maybe we'll even have some kind of a certification program at some point. So there was a couple of questions, not in today's conversation, but on our couple of Facebook groups that we talk about Max and other things. And someone was asking, how Tune works with Max in terms of making good audio systems sound their best by tuning them. And the question was between using one mic versus using Max. And the story I shared with them, and I'll share with all of you now, is that Max is a tool, and it's like a table saw, right? And there's certain things you need to know on how to use a table saw in order to use it at all, right? How to set the blade height, where to put the fans and all that stuff to keep your fingers away from it. These are basic things on how to use a table saw. It doesn't mean you can build anything good with it. You now know how to use it. And Max is similar to that. As you learn how to use the tool, what it can do, what it can't do. And as you start, learning some of the ways that the tool functions, it doesn't mean that you can tune a car. You still need to be comfortable using the tools effectively, interpreting the data, making sure you're making good choices. So Max is not the tuner. You are. It just gives you the data so that you can make really good choices. Just keep that in mind. So just because someone's got a Max doesn't mean they're a pro at it. It's not necessarily the case. It's going to take a little bit of time for people to become comfortable with it. Some people are doing pretty darn good with it already, which is it's given Rob, Matt, and myself a real nice break because they've got it covered. But we definitely have a lot more units out in the field with people that are trying to learn that as much as they can. And that's our focus right now, to get that information out there. These sessions that we've been building upon are kind of little, I don't want to say micro trainings because they're an hour long, but they're highlights on the different distinctions of what Max can do. Not necessarily how to do all this stuff. I mean, Matt did a really good job today of kind of showing how to interpret data and what to do with it. But as we talked about today with the 2 all passes, we did not take it to the next step of trying to correct for that behavior. That would be a separate conversation. So that's a distinction between a tool and execution and using the tool effectively. So
it's kind of crazy when you think about it. We've spent the last 2 years up until this last October just covering the basics of system tuning and audio.
Yeah.
And from October through March now, nothing but tune and Max, and we still are scratching the surface.
Well, it took until March to get to electrical measurements.
Yeah. Yeah, I mean, we have a list and a roadmap. I mean, it's just literally been do for the last couple of months.
It's a lot of stuff. So it's a whole lot of stuff. It's not like you could just take a couple of screenshots and say, here, there you go.
Yeah.
It's a lot.
Here's
to
your
it.
5-page max manual.
And I'll be honest with you, even the targets training that we did a couple of them, I think, on the targets. We covered kind of a broad stroke on that, but there's a lot of really interesting things you could do. And Matt sort of touched on them today, and I was so tempted to make him go down the path. But when he put the all-pass filter on the target to try to mimic what the factory measurement was, he pointed out that there was equalization applied to the factory measurement. Now, technically, in a targets mode, you could apply equalization to try to get it to match exactly. Then you have a simulation of that vehicle as your target, and you could use that for other measurements if you wanted to. So, I mean, it's really, really powerful. And, we've been doing a lot of stuff, Matt and I here playing around, measuring cars and measuring subwoofers. And we could actually model a real subwoofer and do some interesting things with the targets just using the target. I mean, instead of using a subwoofer, we use the target instead and make some comparisons that way. Effectively, it's exactly the same at that point. The phase response would be the same. If you get it perfectly lined up, the phase is the same, the impulse response is the same, the RTA or the magnitude response is all the same in the targets mode. It's really, really powerful. And again, getting really deep into it could take a long, long time. So until next time, thank you so much for watching. We appreciate your attendance, and we'll catch you next time.
Thanks, everybody.
See you, everyone.